Okay.
All right, Josh. Thanks for coming on my show.
Yeah, certainly. I'm happy to be here.
Oh, that's great, because, well, we'll see how you feel by the end of this show. Josh, so we've known each other since 2003. We met at the PROMYS program, where I had my introduction to math. I think you outranked me by a year. Is that right?
I think so. 1 or 2 years. 1 year, I think I was a second year when you were a first year. I think that's correct.
Right, and we both became mathematicians. And so I kind of want to talk to you about the math that you do, about your work, any opinions you have about math education, because I know that's something that you're in, and anything else that comes up. And so we'll just see how this goes. All right.
Yeah.
So so what is it that you do? Why don't you tell our audience what?
Okay, so I maybe should say that with a little history involved for your audience, and you'll be aware of most of this. But I did my PhD under David Rohrlich at Boston University,
Okay.
and that was work on counting art and representations. And then I did sort of the standard postdoc shuffle to a bunch of places. So I spent 2 years at the University of Maine. Then I spent a year at Birmingham Southern College in Alabama, and then 2 years at Iowa State. And then I transitioned somewhat career-wise. So I'm now teaching high school at a prep school, the Hopkins School in New Haven, Connecticut.
Oh, that's a lot of places. That's more places. I only did one postdoc. I see. So I do want to get into all of that. Maybe first I want to know about the math. You're still doing math research, even though you're not in academia.
Yes. Well, I'm not in standard academia in that sort of standard sense, certainly, right?
Yeah.
But I do have a bunch of projects which I'm still finishing up on my own on a bunch of things. But then I'm also continuing research actually as part of my ongoing work. So I should maybe talk a little bit more about the high school that hired me. So they are a quite well-respected school, and their situation is they have each year have a whole bunch of students who have finished the whole standard high school curriculum and then some. So the school has finished all through BC calculus and generally finished some multivariable and linear algebra, which the school also has. And the number of such students is actually growing over time. I actually went to the same school when I was a high school student myself, which I'd like to think didn't have too much with their decision to hire me, but probably did a little bit.
Was it the same people? Were the same people there in charge?
1 or 2 of them actually. So the head of the department who was at one point was now still a teacher, but they switched over departments. And one of the people who hired me was my advisor in 7th and 8th grade. So I imagine in his case that probably worked in the other direction. Is like, really want to hire him? I remember him. He was really, yeah. So, but the reason part of why they hired me. So when I was a student there were a handful of students each year who were interested or capable of doing advanced mathematics. And so one of the teachers there would take on those students as individuals. And after a few years, as the school became a little more STEM focused and students became more accelerated, that wasn't really a practical way of doing it each individually. So they constructed what they called the seminar. And so this is essentially an advanced class each year run for those advanced students, but it's officially in the books as a class. And different teachers have run it on different topics or different things. So the way I was hired in part because I can run it. And the person who's done it most often previous years is retiring, actually just retired. But so the way I've done it is I've run it essentially as a seminar where the students focus on proof-based mathematics, presenting, coming up with ideas in the first semester. And then the second semester, we take whatever was the major topic of the class, and we try to do a little research project on it. So the year before this one, we did number theory, which is my own area of expertise. And then we actually had a lot of kids in the seminar that year, a lot of students in the seminar. I think we had 9 total. So we actually I broke them up into 2 separate research projects. And there was some degree of sorry.
How many students take this advanced?
So most years fewer than that. I believe next year I think I'm going to have 4 or 5.
Oh, so you can do this for 4 or 5 students, and what was it, 9 before?
9 last year. 9 was a little high, but so
but
this
smaller than a typical like high school class.
Yeah, look, one of the advantages of a private school is you can do things like that. But then so this year we did graph theory, and then we did a research project on what we call total difference labeling. And we it's a variation of coloring notions of chromatic number for a graph. That has some and we extended it to certain nice infinite graphs in some other contexts. So that was the second semester research for that. We only had 4 students in it, so that was really easy to do, and they actually had really good results. And so we just sent them. I just no, I don't know, it was morning or yesterday. I think it was last night. I sent over our version of our results that's been now nicely written up to one of the people who originally came up with the idea of total difference labeling. And so he's going to hopefully take a look at it, and hopefully the results are good enough to get sent to a journal, but we'll see.
Oh, so that's impressive. So you say that these high school students, you can get results published in real journals.
Well, I mean, I'll hope. We'll see. So the journal we're aiming at for this one is Involve, which is a journal which is mainly aimed at undergraduate research projects, right? So projects undergraduates do with their professors. So it's not like I'm aiming, we're not aiming at, the annals here. Right.
I actually think, the undergraduate REU that I did, that paper was published in Involve.
Right. So it's about that level of, it's possible that if we really pushed it, you could put the research they did in, a graph theory focused journal, but I don't think that's really, there's not a need to aim for that sort of thing there.
Well, since you discussed it, I mean, what is your experience? What's different about teaching, say, in the kind of schools where you did your postdocs versus this high school? I mean, it sounds like the students are.
So one of the biggest differences is class size, right? So, right, when you're teaching at these big state schools, you could have 100, 200 students in an introductory calculus class.
You were teaching those like big lecture hall classes.
Yeah. Right, so I did do that sort of stuff, that sort of thing for, I think for Calc 1, Calc 2, Calc 3, some other classes. So one of the big appeals and one of the reasons I was tempted to switch over was that it was, I just noticed that really looking like the stereotypical mathematician if I can't even keep my collar correct.
I can't even remember the last time I wore a shirt with a collar, frankly.
Yeah, well, I figured I'd give you the minimal respect to wear a collared shirt, but then apparently not the minimal respect to bother making sure that the collar was roughly symmetric. So somewhere in that mid-range there, I guess.
Continue.
Anyway, as I was saying so I taught classes like that, and one of the big appeals to teaching in a high school level is much smaller classes. That's a big appeal. And one of the big appeals at teaching private schools, you have not just smaller classes, but you have, especially in a school like this, very strong students, some of whom are very dedicated, whose parents are really dedicated also. And so when you have issues with a kid, with a student, you can actually get the parents to, push them a bit. It's not the same thing at either teaching like, at a college level where that's not really as much of a thing, or for that matter, teaching at like a big public school where a large fraction of your students who have trouble, there's often family issues. Now, that's not to say we don't have any students who don't have issues at home, but it's not as common. The other issues there, yeah. So it's and a lot of the classes I'm teaching are in practice very similar to what I taught in college.
But the student, their work is different, or their attitude is different. You actually
Attitude is, I would say, mostly harder working. There's some exceptions, obviously. You can't make a complete generalization, and there are other complicating factors, right? So if you're teaching, classes other than the seminar, for example, second semester senior year, yeah, the seniors just aren't really very productive. That's just life. I mean, not all of the seniors, I should be clear. Some of them remain very productive, but a noticeable fraction don't.
I mean, do you have more autonomy or less in what you teach, how you arrange the course?
I would say it's about the same depending on the class. So, so I've taught pre-calculus, and so you have some degree of autonomy there. But at the end of the day, we have a shared final exam, and that's pretty similar to how things were done when I taught that sort of class at a university level. For other things like the seminar, I have a massive amount of autonomy, but that would be similar to if I were teaching, an upper level class at a college. So, I did teach number 3 at Iowa State, and I taught intro abstract algebra at University of Maine. And so I had some degree of flexibility. Here I have more because the seminar can be on absolutely any topic, right? So it's, what do I want to teach this? What do we want to do? So first year I did it was number theory. Then last year we did graph theory. We're planning on doing knot theory next year.
That's a lot of responsibility on you to mold these young minds.
I wouldn't say mold. I thought you were going in a different direction. Responsibility, I was thinking to pick a topic that I can do well, right? I've never taught knot theory before.
Yeah.
So I wouldn't say molding them as much as responsibility for picking a topic where really I can do it well enough, they can do it well enough. And since I'm trying to do these second semester research projects, other people who've taught the seminar previously haven't really had that sort of research aspect. To make sure.
I'm thinking, even if you have a small class, that's a hard thing to do. It's almost the equivalent of like advising a senior thesis and teaching a class.
Yeah. I mean, look, for the research topics, I can say also, one of the things there is I'm actively, it's not like they're just researching and I'm, the advisor who they pop in once a week for that sort of stereotype. I'm, in the trenches with them working on it. So if the paper, that we're working on, I would say there are 4 or 5 ideas in there. 4 or 5 total ideas in the paper, that really substantial ideas. And I would say 2 of them were mine and probably 3.5 of them were theirs, in terms of the major trends. So,
and you're the one who picked the problem. You had to figure out what was doable, what was appropriate.
Yes. And so one of the difficulties here actually is one of the things I'm actually worried about next year a teeny bit, is if we do try to do the research aspect the second semester, is so I'm a number theorist by training. So I have a pretty good idea coming up with number theory problems, being able to tell where there's probably some room there. It's not just that. Also, I like to think of myself in general as coming up with good questions, but but then last year, we did graph theory, as I said, and my final position before I transitioned was at Iowa State, and they are considered to have a very good graph theory department. By some accounts, one of the best on the planet. And so the weekly colloquium there, and various stuff going on there, often was graph theory. So whether I liked it or not, I absorbed a lot of graph theory for those 2 years. Knot theory I have less on, so I have some background in it, but not nearly as much. So it will be interesting to see. So one of my summer projects is to start looking for good research problems there.
I guess back in my history, I took a class on graph and knot theory from David Rohrlich, from your advisor back at PROMYS in 2004. So
are you sure that was David who did that? I thought it was it was David. Okay.
Right.
I remember. I think that was 1 year was done by Ira Gessel. Would have been my I think, but maybe David did it a different year.
Yeah. What about your teaching load? How does it compare?
Load's a little higher in terms of teaching load. right? So, having 3 preps is standard at a high school level, roughly, that's a little high from the college standpoint. But so there's that.
3 preps, sorry, that's 3 courses you're teaching.
No, so a prep is distinct. So maybe I'm not, so a prep is you're preparing for some number of copies of a class, right? So for example, say someone taught 1 geometry, 2 pre-calculuses, and say a calculus. So that would be 3 preps because they have 2 copies of pre-calculus. So they functionally, the preparation is about the same for those 2.
All right, so you're doing more, teaching more classes than you were when you were teaching at university. And
correct. And also when you're teaching at a high school level, there are other expectations, right, in terms of coaching and other duties. So I was actually an assistant wrestling coach 2 years ago. This last year, that didn't happen due to COVID, so we really couldn't run a wrestling in a normal fashion.
Wait, I didn't know you did wrestling.
Yeah, I did it when I was in high school. So yeah.
Are you a good wrestler?
I mean, I'm good enough that I can coach. I was assistant coach of 7th and 8th grade. It's not like that's yeah.
I guess I know nothing about wrestling. I did some MMA and some boxing.
It's substantially different. I would say it's closer to MMA than boxing, but it's not very close to MMA.
That's right. We did a little bit of grappling on the ground, just trying a couple of things. I didn't devote myself very fully to it. And boxing, I was.
But no. So the point is, there are other obligations one has.
That's why I wasn't even thinking that. I was thinking that you have to do your own grading, which is something I.
Yeah, but you have to do a lot of your own grading at college level, also, especially for advanced classes. So, like when I, did number theory at Iowa State, I had a grader who could help with the problem sets. But at the end of the day, if you're doing proof-based stuff, it's really, really helpful to actually be looking at a lot of the stuff yourself. And
I was able to get, have grad students to grade the homework, and then I did all the tests.
Yeah, and it's a similar setup there. But yeah, so that's definitely one aspect that's different as you're looking at it. Now, one of the things you can also do, because you have small class size, is you can do things where they help grade each other and figure things out. So one thing I'm very fond of, I've done this bunch for pre-calculus, is having, and this really requires a small class size, is you have each student go up to the board and they put up one of the problems from that night's homework on the board, and then everyone walks around the room and they put a check mark next to it if they agree with the solution or whatever. And then if they don't, they can make a little comment either with like a post-it note or just add a question mark if they want to talk about that problem. And then you can go through the whole homework that night, that day, 10 or 15 minutes at the beginning of class, and it works well and it gets students talking if you do it right. So you can get through homework that way without actually giving it a grade necessarily. Even then and then you can also just be like, I will occasionally collect homework, and you collect it, a handful of times, enough to, get an idea that they're doing it and, encourage it. But, and you get a good feel for who's actually working or not when you do that sort of thing.
I see. Something I guess I noticed teaching at the university, we're not expected, we don't have to be too invested in whether the students succeed. If a lot of people do very poorly, it makes you look bad. But there's very little observation that you're not under a lot of scrutiny there, which I imagine you are.
I think that I would say, without saying any specific universities, I think that varied a lot from school to school I was working at. So there's a lot of, I think there's a large variation there, but I would say that it is true that there's substantially more scrutiny at a high school level. And one of the things you also have when it's a private school is you have some parents and some students who sort of have an attitude of, I am paying your school X very large sum of money, my student should do well. And that viewpoint, I would say, is rare. It exists, and you do encounter it on occasion, but it's rare. But yes, you do have, and there's more reasonable versions of that, just like this is a class of 12 students. My student is having trouble, my kid's having trouble. Can you please figure this out and make them stop, work with them? So there's variation there. And certainly you have less of a problem. So when I was, teaching university level, you had some students who just, for lack of a better phrase, would just fall through the cracks, especially at the big universities. And sometimes you would notice it, because you'd be doing well and be like, well, that person hasn't shown up to class. And then you'd be like, well, what's going on? And then you could try to do something. But the degree to which students, having trouble, either just academically or mental health or other issues, it really was highly random, and even students, even schools that had, seemed to have a functionally on paper good safety net, sometimes it just didn't work quite right. I know that's a mixed metaphor with falling through cracks and safety nets, but I think the idea should be clear.
At Cornell, they really do have those safety nets on the gorges, because they used to have a problem with people jumping off of some bridge.
Right, so then in case it's a literal safety net and a literal crack. No, I was gonna say, look, I did my undergrad at Yale, and I actually had some very serious mental health problems my junior and senior years. And in that case, there really was a substantial safety system in place that really did help out a lot. But I do know also from talking to other people who did their undergrad at Yale and had problems that some people found the system to be actively unhelpful. So.
Well, I might want to say more about education later. I just want to know, do you have time for your own math research?
Yeah, so I'm finishing up a paper which I started on Weil on. So one of the things I believe you described me, although didn't name me, as the person in one of your earlier videos who was
I did.
with
one of the reasons I wanted you on, and that wasn't really so nice of me. It was just something that occurred to me.
Okay. Anyway, I should say just to the viewers, for Dan's describing past as a person who's obsessed with odd perfect numbers. And that's not, I don't think that's quite fair. And certainly the fact is that's certainly is one of my major areas of research. Look, and I'll be honest, one of the appeals also to being in a high school environment is I can do whatever research I want. And hey, if it's nibbling at tiny, tiny pieces of this big unsolved problem that we are nowhere near solving and I'm not going to solve either, well, it's not like my publication rate or degree is, responsible for anything else I'm getting.
Well, that's okay. That's a lot. I want to talk about a lot of that. So why would you go after a problem? What are your research goals given where you are? If you're not in academia, as you say, you're not under the same level of scrutiny or pressure. But in my view, wouldn't you want to? Now you need to do something big to get back in, to get those people to give you that respect.
I'm having fun. Is my primary thing. If I'm doing research and I'm having fun, I'm enjoying, I'm thinking about it, then that's great. But one of the reasons why this problem, I should say, interests me in particular, it's not just because of its age, although often we could talk about it's often actually.
Okay, well, how about this? How about you say, because I've had a couple of people do this, why don't you try to explain what it is that you work on first, the way you would explain it to like a lay audience, and then maybe we'll get into some more.
All right, so I'll focus on this specific problem because it's the one that I'm apparently infamous for based on your previous.
Well, I was speaking abstractly about a person could be doing work like this.
Okay, abstractly, right? Okay, so we say a number is perfect if it's the sum of all the divisors of the positive divisors of the number, which are less than a number, add up to that number itself. So the smallest example of this is 6, where the divisors are 1, 2, and 3, and 1 plus 2 plus 3 equals 6, so 6 is perfect. An example of a number that fails to be perfect is 8, where the divisors that are less than 8 are 1, 2, and 4, and 1 plus 2 plus 4 is 7. 7 is not equal to 8, so 8 is not a perfect number. All right, so these numbers have been of interest since the ancient Greeks. And arguably two of the oldest unsolved problems in mathematics are twofold. Are there infinitely many even perfect numbers? And is any number odd and perfect. And we don't know exactly how old these problems are, either one. Part of the difficulty is that it's only in the last few centuries that people have really gotten to the habit of explicitly saying, here's writing down, here's a question I'm thinking about that I don't know the answer to. And so to know what the
ancient... You say it goes back to the Greeks. I mean, so that's a long period of time. Do you know anyone in particular who mentioned this, just out of curiosity?
Right, that's the thing. So the first person who explicitly says, is there any odd perfect number that we have that's unambiguously, that's the question they're asking, is Descartes. And he's very recent, right?
Yeah.
Only about 300 years or so. A little over 300 years. Actually, maybe closer to 400. Somewhere around there. But if you look at the ancient Greek sources like Euclid, so Euclid does a lot with perfect numbers, right? So Euclid shows that there's a certain way to construct them from Mersenne primes, which are primes that are one less than the power of 2. And then it would be much later, Euler would actually show that all even perfect numbers came from Euclid's form. But if you look at what Euclid's doing, for example, it really does look like one of the things Euclid is trying to figure out is, hey, are there infinitely many of these?
Yeah, okay. So I'll grant that to Euclid. If he's writing about perfect numbers and he already showed that that they could be of a certain form, I think he deserves that credit. Or maybe I know that he was doing a lot, recording a lot of stuff that other people had worked out before him.
Right. There's a lot. I think there's some. I'm not an expert on these things, but I think there are consensus a very large amount of what Euclid was doing was writing down what were known results in his time period.
That's like 300 BC.
Is that around then-ish? That sounds roughly correct. And then there's someone a few centuries later by the name Nicodemus. Who writes a whole bunch of things about perfect numbers, some with no proof, some of which are correct, some of which are incorrect, some of which look like he's misunderstanding things Euclid wrote. And so he says like all the perfect numbers are even. Do you count that as like, I'm wondering about this question if I've just stated that as a fact? Like, what do you do with that?
It shows that someone's thinking about it. Yeah,
it does suggest that people are definitely
anyway.
Yeah, right. It does suggest people are definitely thinking about that. Nicodemus has some other things. So he claims that like they alternate, and I think if I remember correctly, that they alternate ending in 6 and 8, which is just wrong. I mean, but if you go through the first few, that looks empirically right, and then it breaks down.
Isn't okay? I don't remember. What are the? Is it
6, 28, 496, 8128. The next one is 33550 I don't know if that would have been known to Nicodemus or not.
Even though that's of the form that Euclid had.
Those are all the right, but it's bigger. So the difficulty is, so the next obvious candidate would be. So it turns out they needs that you get them from these Mersenne primes. Primes of 2 to the n minus 1. And the difficulty is that, so it turns out that if 2 to the n minus 1 is prime, it turns out that n has to be prime. And this comes from a factorization argument. And one of the difficulties is the next, so the first few Mersenne primes you get are coming from 2 to the 2nd minus 1, 2 cubed minus 1, 2 to the 5th minus 1, 2 to the 7th minus 1. The next example, 2 to the 11th minus 1 actually turns out to be composite. It's 23 times 89. All right. Anyway, so that so I don't think 2 to the 13th minus 1 being prime was known. I don't remember what year that was. I'd have to go back and check when that's discovered.
Well, there's this sieve of Eratosthenes, and Eratosthenes was in the
right. So, but 2 to the 13th minus 1 is already impractical unless you're willing to spend a lot of time on it to do the Eratosthenes sieve. I think it is like classical. So I'd have to. I mean, it's the sort of thing you can probably look up. My guess is if you go to the Wikipedia article on Mersenne primes, they'll say exactly when it was found. But I don't remember. Yeah. Anyway, so the point is these questions are very old. And so the question about odd perfect numbers interests me. And one of the reasons it interests, a bunch of reasons it interests me. And one reason is that it turns out a lot of what you're doing naturally connects to good things which are worth thinking about. So it turns out to be closely connected to distribution of primes. It turns out to be connected to a lot of the behavior of cyclotomic polynomials turn out to be intimately connected. So a cyclotomic polynomial is a polynomial whose roots are the kth primitive roots of unity. And so, so that turns out to be a very natural object that we care about in a lot of contexts. And it turns out they're closely connected. But one of the reasons that actually interests me also as a problem is because we've overreacted. Here's what I mean. So there is generally a good attitude among mathematicians. And that is, if a problem is famous and open, don't spend much time on it because it's probably really hard and all the obvious stuff has been done, right? So, you see this, with, you've ever talked to an undergraduate math major who's like, I want to prove the Riemann hypothesis, or I want to resolve P equals NP, or even I just want to prove the infinitely many twin primes. So, any of these famous sorts of problems.
That last one, is not such a unreasonable research goal today, I think. But
it's not as unreasonable as it was before Yiting, Zhang, and Maynard's work, but it's still very, very far from where we are. But the upshot, right, is, we tell them, and we tell them correctly, this is not a good goal. Spend time on little problems. If there's a piece you can cut off, maybe work on that. But even then, maybe spend time on something adjacent to your problem. The truth is that this is very good as a rule, right? You're not likely to get that far with any of these problems. In my viewpoint, though, the odd perfect number problem has had too much of that attitude, in that there are a lot of good techniques out there which can be used to apply, not to solve the whole problem, we're nowhere near that, but to cut out little pieces of the problem more effectively. And I think that because it's such a famous problem, that instinct that the professional mathematicians that we all have of let's go work on other stuff may be operating a little too strongly.
Well, okay, so I agree with you that that is advice that people give, and I think for good reason, because you need problems starting out where you'll be able to make some progress with the things that you have. On the other hand, that goes against the, in order to establish yourself, you will need to do something that people take notice of. So you somehow have to chart the right path. I guess I'm wondering, when it comes to this problem, so you really are working on this problem of, you want to get at the question ultimately, are there either infinitely many perfect numbers, are there any odd ones? So
right, and I have much less focus on the other infinitely even ones. For a bunch of different reasons, that problem I think has much less low-hanging fruit. I think that I think the instinct there is mostly correct, right? Is that I think as far as I can tell, all the obvious stuff for even perfect numbers and Mersenne primes has basically been done. I think in the odd perfect number case, there are lots of different directions to go, where there really does look like there's a lot of room to, and a lot of connected low-hanging fruit. And again, it's low-hanging fruit that connects to things like cyclotomic polynomials, distribution of primes, and the exact error term on the prime number theorem, and things like that, which we should care about anyways, right? Even if there's some of the problems you're coming up with, right, problems that become connected or questions that arise, are things where if you tell people and you don't tell them that motivation, they'll think that they'll listen to it for a few minutes, and if they're number theorists, they'll say, yeah, that seems like a very reasonable, interesting question.
Yes. Okay. So that's good. So, I mean, the things I would look at, say I'm the guy who has to decide whether to fund you, and you said,
don't fund me.
Don't fund you?
Don't fund me. They're well, first of all, I mean, not sure we should be funding much pure mathematics to the start. So that's my opinion.
Ooh,
I think that from a utilitarian standpoint, there's a lot of other stuff to fund. But if you are going to fund pure math, I think arguing to fund this would be one of the tougher ones to argue.
Yeah, because you have to say, I mean, I'm interested both in the, how likely is it to be successful, but also what is the meaning of it? What is the significance if it is successful, or at least even the work along the way?
Right. So I think, okay, so maybe I'm selling myself a little short, right? So one of my papers, which was recently accepted on this, a major part of that paper ends up connecting unperfect numbers to a somewhat natural version of what I would say is a version of essentially Mertens theorem over short intervals.
What's that?
So I don't know if you remember Mertens theorem. So Mertens theorem says if you take the product of primes p less than equal to x, and you're multiplying p over p minus 1, that there's an asymptotic for that quantity. So it's p over p minus 1 is the product. So this is asymptotic to a constant you can write down explicit. I think it's like e to the gamma, where gamma is Euler's constant log x, where the primes less than equal to x. So it turns out that actually can be formally shown in a certain technical way, this theorem is weaker than the prime number theorem. And in fact, it was proven a few years before the prime number theorem was proven. And the way it's, in that sense, you can write down sets that look a lot like the primes, that satisfy that relationship, but don't satisfy the prime number theorem. But anyway, so one of the things, but it turns out to be a very natural sort of way of trying to understand primes and the distribution. And so one of the things that came out from my work was looking at, and this is actually something that others have studied before in other contexts, what happens if you restrict p over p minus 1, where you take the product from primes between x and y, between two values, and then you can ask questions about how that sort of function behaves. In a certain sense, although you have to be more explicit, what I actually cared about was an inverse of that function and approximating that. And there's a lot of detail there.
This is a part of analytic number theory I really haven't looked at in a long time. Yeah. What about, so I guess I want to know what techniques can you use? So these are the problems that are sort of adjacent to the odd perfect number problem, is what you're saying.
Right. Yes, right. And so the things that are adjacent there are, standard analytic techniques, using, zeta functions, things like that. Although honestly, I don't understand the zeta function end as well as I should. And then things like sieve theory. So there have been a whole bunch of papers using sieve theoretic ideas to try to get a better understanding. I would say the two people who've probably done the most in that, and some of it's been quite impressive work, is a fellow Tomohiro Yamada, who's also done a bunch of other very good sieve theory work, and completely separate from this. And then the other person would be Pace Nielsen, who's also done some connected work.
How about this? Let me ask you this. If you had a solution, if you knew the answer to this odd perfect number problem, and I assume you think there are no odd perfect numbers.
There's a heuristic due to Karl Pomerantz which strongly suggests there are none. I would be shocked if there turned out to be one.
If you knew that fact alone, would it imply anything that other people care about in number theory?
No.
Okay.
Not particularly. That should be clear, right? It's really the adjacent connections which lead to interesting aspects of it.
And so can you say what are the consequences that you think may come out of the investigation? Or
so look, one of the things we're always concerned about is just trying to understand the distribution of the primes more. We're trying to understand cyclotomic polynomials more. We're trying to take sieve theory and make our sieves, finer. I think finer is the word I'm looking for. Trying to do all of that. Right. And to some extent, I'll use a different example, right? Let's take the twin prime problem, right? So in fact, right? If you ask people, well, if we just knew there are infinitely many twin primes, what would we get out of that? And the answer is not much, right? So we don't have any obvious way, to go from infinite many twin primes to, say, the Elliott-Halberstam conjecture, or Riemann hypothesis, or Lindelof hypothesis, or any of the things that we use to go in one direction. And we wouldn't even get like sieve things out of it. But the work on improving, the sort of Yi-Teng-Zhang and Maynard Maynard-Tao sort of results on the sieve end has led to sieve improvements in the general sieve theory there, which led to a lot of other interesting things.
Actually, can you say?
So sometimes you focus on one problem. Yeah.
Can you say what are these modern sieve methods? I mean, I only know the sieve of Eratosthenes, so.
Okay, so I'm not a sieve theory expert, although I've been trying very hard to really get to really a better understanding of the sieve methods. So with that disclaimer out of the way, essentially all of the sieves are attempting to generalize Eratosthenes sieve. And they all use a very similar thing, is that fundamentally what Eratosthenes sieve is doing is a counting argument. And so in the when is Legendre? Is he like 1700s,
Late
early 1800s?
I think.
Okay, whenever Legendre is around. So Legendre comes up with what we call Legendre's sieve. And it's essentially Eratosthenes sieve, but counting really carefully. And so he comes up with a way where if you know all of the primes less than the square root of n, you can find exactly how many primes are less than or equal to n without doing the entire Eratosthenes sieve. And essentially, he's doing an inclusion-exclusion argument. Yeah. And then he actually generalizes that. And I believe, I'd have to double check, it's either him or someone building on his work, actually is the first person to show that the number of primes less than or equal to x is little o of x. That is actually, it's not a positive proportion, which seems like an obvious statement, but was not actually proven before then to mine, as far as I'm aware. And so in some sense, all of sieve theory is inclusion exclusion, right? So, if you need someone to ask you to teach you sieve theory standing on one foot, you tell them, everything is inclusion exclusion, the rest is commentary. That's a rough summary of it, but it gets really, really, really subtle. And some of what they do involves what they call weighings, which in some sense are a generalization of inclusion exclusion. So there's a lot going on there. But then, so the next step actually in this context was Brun. So in the early 1900, I don't have the exact year, but I think I want to say 1910-ish. So Brun came up with what's now known as Brun's sieve. And Brun's sieve used, again, a more clever inclusion-exclusion argument, and he was able to get a much better handle on twin primes. And so he was able to show actually upper bound how dense the twin primes are. And he got it to be upper bound dense enough that he was able to show that the sum of the reciprocals of the twin primes converges. Mm-hmm. And the relevant point here is that the sum of the reciprocals of the primes diverges. Yeah. So this really, the twin primes are rare in the set of primes is sort of the lesson from that. Yeah. And then his sieve got tightened a bit by him and some others later, actually get a explicit upper bound on the rough order of number of primes that twin primes. That's in fact the correct upper bound. Like there is a conjectured asymptotic formula, and his is the correct upper bound growth rate up to a constant, multiplicative constant. And so that was really the start of the modern sieve theory. And everything else after that was then building on Brun's sieve. So Selberg did some work, and a lot of other people. Yeah.
Okay. I guess I'm wondering whether you think that problems like whether they're odd perfect numbers or the twin prime conjecture, I guess you think well, they're good tests for whether we have the right theory. We should be applying techniques. If we try to solve them as we know our techniques are good if we can solve this thing, but we're really trying to get at something else. Is that how you see it, or?
I that's how partially how I see it, right? I think one of the things when we construct things like sieves or really good understandings of the distribution of the primes and things is we're trying to construct structural things which show that we have a really good understanding, right? So I'm going to use a toy example. So I'm guessing that most of your viewers have seen modular arithmetic.
Okay, maybe that's
Does that seem fair? Okay, for the viewers who have not, it's looking at, well, go Google modular arithmetic, pause this video, and then come back. Okay, it's not that complicated.
Arithmetic on a clock, but the clock could have not just 12 hours.
Yeah, right. That's how we would normally say it, right? It's a clock arithmetic, but you can also do addition and multiplication, and you just care about remainders. All right. So the very first uses of modular arithmetic, in some sense, we're just looking at parity, even in oddness, right? So the ancient Greeks, ancient Chinese, a bunch of others were able to do stuff there. It's not until I don't have the exact year, but sometime in the Middle Ages, people start thinking about, oh, we could look at remainders when I divide by 3 or 4 or 5. And then the first really non-trivial use of this idea of looking at remainders and looking at modular arithmetic, although it doesn't have the modern notation.
I think that's not true, by the way. I think there are ancient examples of a lot of that.
Possible. I'm not a historian of mathematics. I could have.
I want just one quick thing. Have you ever heard of Archimedes' sun god's cattle problem?
Oh yes, so yeah, that's a good point. So yeah, so okay, so certainly they had some versions of it. Yeah, that's a good example. So you know much more generally the history, and as it's shown also in an excellent video you had on the rise of the logarithm, which I really thought was fascinating. I learned a lot from. Yeah, okay. So I guess I'm getting
fair praise coming from you, I think, because you've always told me how much of a fool I am, but
I don't think I've ever said you're a fool, did I? Did I maybe when you were promised, did I use that language?
But that's okay. I was a fool about a lot of things. But thank you about that. Yeah, I think people should.
No, I enjoyed the video quite a bit.
History of
I'm not sure you should be relying too much on what 17 or 16-year-old me said to you in terms of but.
I haven't done a video. I'd love to do a video on some of that number theory and the sun god's cattle problem, because it's clear that Archimedes, in order to try to approximate pi, had basically solved what we today call Pell's equation.
Yeah.
But whatever.
All right. So your point with Archimedes sounds the sun cattle problem actually undermines part of what the claim I was going to make. So I'm going to continue with the claim, but acknowledge it's not quite perfect. No pun intended. So then Gersonides in the 12 or 1300s proves that there are no powers of 2 that are 1 away from a power of 3, except the obvious pairs, 1 and 2, 2 and 3, 3, 4, and 8, 9. And he does that partially by thinking really carefully about modular arithmetic. Mm-hmm. Right? But that happens sort of like, again, it's like a few people like Archimedes and Gersonides, these very, very bright people come up with just the right, modular arithmetic they need to do that. And it's not really until Gauss comes along and says, I'm going to do this systematically. Here's good notation for it. Here's how to think about it in the general case. Here's some good lemmas about what happens in general. Here's some good ideas, also essentially heuristics on if you've got, something you want to solve, what's a good modulus to pick, things like that, to the point where, we can give beginning undergraduates or high school students or whatever problems that are Diophantine equations or similar things where you can do a lot just with the modular arithmetic.
You could even give them Disquisitiones Arithmeticae. That's a great book that I only looked at recently. I think I should have. I feel like you could start people with that book.
It might be interesting to start. I'm not sure I would do that from a pedagogical standpoint. It might be interesting to see what happens. I think
Because he's figuring it out. He's developing it all.
Right. He's still, and there are a bunch of things that even from a modern standpoint, it seems like, well, why would you phrase it that way? We have a better phrase, so it's not quite. So Edwards, who wrote an excellent book on the history of the Riemann zeta function, is very fond. Actually, I don't know if he's still alive. So
no, you know what? I actually tried to get him on my show.
Okay, is he? So he's still alive then?
No, his widow wrote to me, unfortunately.
Oh, okay. Because I wasn't sure. He's very old now. Then he isn't. Okay, so he was.
He's written some of the greatest books, by the way, and not just.
I talked to him many years ago, but I hadn't kept in touch. So I don't know when. When do you know when he passed?
Just this past November.
Oh, okay, very recently. He had to have been quite old, though. I think I talked to him, actually not that, like 6-7 years ago. Anyway, but he was very fond of arguing that we should all actually go read, the originals. So he, read, Riemann's work in the original, read Gauss's work in the original, etc.
Yeah. I should just say for my audience, and I'm going to make some videos about his other books, but his books on number theory and Galois theory are so excellent, and they're such a radical departure from how these courses are taught in an ordinary math program. Yeah. I actually think that's his way is the right way. Building up. I'm
not sure about that, but it's interesting. I'll say that. It's certainly an interesting way. I think a lot of what he does certainly is a very good compliment if you've seen them already in a standard fashion. But although he did have one or two weird notational insistence, like his book on the Riemann zeta function, he, instead of normalizing the gamma function in sort of the standard way, so it's one away from factorials, he uses this other function that's normalized, so it's exactly on gamma, which is fine, except it's like, is this the hill you really want to make your stand up?
That's not so important. There are these idiots on YouTube who care about the normalization. They want the key constant to be 2 pi instead of pi or whatever the.
Oh, I think that the people who are doing that, I think tau is it. I think that's mostly tongue in cheek.
Oh, okay.
At least that's my impression. I think there was actually a decent argument for it, but I don't think it matters. I think there's a pedagogical argument that it would actually make some sense when teaching the unit circle, I think. But it
doesn't matter at all. I think
it's mostly tongue in cheek, though. But I don't think any of them really believe it that strong. I think it's also more of an.
Edwards' other books, though, as better than the modern, very formal approach to algebra. Yeah. That's a subject for a different day. Maybe.
Yeah. I find that actually interesting because it seemed to be you used to be very heavily interested in formalism as the approach to heavily formal attitudes. So that's interesting that your attitude on that seems to have changed. What?
You mean when I was 16 or 17? And
yeah, about then.
That's true. I did not only when around the time I was finishing my undergraduate was did someone sit me down and it was like, what math is important and why would you want to do this kind of math as opposed to another kind? And then I had to see it as a grad student to form my opinions. But that's not the conversation we're talking about.
Sorry, I actually was trying to make a point about modular arithmetic.
Okay.
So the point about modular arithmetic I was going to make was that, so to some extent, right, what Gauss did was gave us a structural understanding that gave us a really good understanding of basic aspects of the integers. And part of the way we see that is now that there are all of these problems where you can glance at them and be like, oh yeah, just use modular arithmetic and see what happens and it will probably work. Okay. And so to some extent, that's the same thing we're doing with the sieve theory or anything else. Like the sieve theory, we're building up on, we're mostly focused and aiming at the twin prime problem, but there are lots and lots of other problems now where, the sieve theoretic methods are, if we get them strong enough, hopefully, it will be at the point where we can just be like, yeah, throw some sieve theory at it. Although the sieve theory is much more abstract than modular arithmetic. And so that gets you a sign that you really do have a good structural understanding, is that there's this broad class of problems where you can sort of tell at a glance, do this method, and it will probably work.
Can you say a little bit about what sort of, any more specifically, what sort of math is involved in these techniques, what you need to use? What kind of analysis?
For the sieve theory or for the odd perfect number problem, or
Yeah,
the
either.
sieve theory, I'm not sure I'm qualified to say more about. I mean, but I'm sure you can probably find a good sieve theorist to get on your show and give you a really good talk on that.
Well, all I'm asking, forget about this. See, you could tell me odd perfect. I'm wondering, is it? Are you using advanced stuff in complex analysis or special?
I mean, you're not directly, right? Because like when you get back, I mean, certainly I'm not, partially because honestly, I'm not very good with the complex analysis, but there are people who are trying to do so. So like one idea, for example, that I've actually had an idea since I was for a long time about actually doing it directly, maybe solving the whole problem using a sort of complex analysis approach. Because what you can do is you can make a Dirichlet series of sigma of n, if sigma of n is the sum of all of the divisors of n, that is including n itself. So right, earlier we were looking like for 6, we're looking just 1, 2, and 3, but this would look at 1 plus 2 plus 3 plus 6. So in that case, this turns out to be the normal way of talking about, like the natural way of talking about things like perfect numbers for a whole bunch of reasons. But it turns out that you can then make a Dirichlet series from where the nth term is sigma of n minus n all squared. Oh, sorry, sigma of n minus 2n all squared.
You need some kind of multiplicative function, is that right?
Right, sigma of n is multiplicative, which is part of why it's very nice in a bunch of ways. But sigma of n minus 2n all squared turns out to be a Dirichlet series that you can write down explicitly in terms of the Riemann zeta function, in a pretty straightforward fashion. So you can write down the Dirichlet series explicitly in terms of the zeta function. And so now if you could just do like complex analysis, because hey, we can do complex analysis to Dirichlet series to recover their coefficients and just evaluate them and maybe show that all of the terms that are 0 are even somehow, right? And that sounds plausible, right? And I've tried to do that on and off for a long time, and I don't know complex analysis well enough to get that to work. And I mean, my suspicion is that that doesn't work and that there's just a dead end. But I don't really know enough complex analysis to be sure. I mean, it's possible that if you got someone who's really good on the complex end and they spent a year or two on that problem, they might actually solve it. But I haven't been able to persuade
modular function or form or
yeah, there's definitely some connections with modular functions. And so people have proven some aspects about sigma of n and about perfect numbers using modular forms and those sorts of identities you get from there. But there are two disclaimers I need to make about that. So one is, it turns out a lot of not all, but almost everything people have proven using those methods, it turns out you can then prove with more straightforward elementary ones. So for example, there's a result that an odd perfect number has to be either 1 mod 12 or 9 mod 12, I think. And this was actually first proven using like it's called Toshard, by a fellow named Toshard back in the 60s, using like very sophisticated modular, clever tricks involving modular form identities. It turns out there's a 2-paragraph proof of this you can write down that someone else whose name I'm blanking on her name right now, but found like a few years later, and other people discovered separately. That's really just absolutely elementary, the point like Euclid could have discovered, well, maybe not Euclid, but certainly Euler or Descartes could have discovered. And that's true for a lot of it. There's been a whole bunch, I wouldn't say a whole bunch, but a few papers where people have been like, hey, I proved this thing about odd perfect numbers using modular forms. And then it's like, well, now that you've proven it, maybe it's good to know, but we can not too hard to come up with a elementary proof. So maybe there's that. The other disclaimer, and one of the difficulties is sums of divisors show up in modular form coefficients all the time, but there's a problem. The ones where they're naturally most well behaved aren't sigma of n from modular form standpoint, but things involving sigma sub kn, which is the same thing, but instead of looking at the sum of the divisors of n, you look at the kth powers. And so sigma sub 2 of n, sigma sub 3, et cetera, have lots of beautiful, beautiful identities. And there's a lot of machinery there. It turns out to be connected to a lot of structural stuff in modular forms. Sigma of n from a modular form standpoint is less well behaved. And so that's part of why there are fewer things that are really working well there.
I guess my inclination would be that those, that theory of modular forms is very powerful, and especially if they parameterize something that has some algebraic geometric significance.
Right, there's a lot going on there, right? To some extent, I think this is an example of the ancient Greeks inadvertently hit upon like the tough case somehow is the problem to think about. And that there's sort of, so there's things going on there. And the,
what do you mean?
So I mean, that's part of what's happening.
What do you mean they hit upon the tough case?
Well, so if you want a lot of questions you can ask about sigma sub k of n, you can answer using modular forms. And I don't want to speak, I'm speaking in vague generalities. And so my guess is that someone will comment on this video, well, maybe that's not quite right. So I'm going to be clear, I'm speaking deliberately.
I think mathematicians are way too careful. They say very little because they
Okay, fine. So I'm just going to say there are a lot of natural questions you can ask about sigma sub k of n. If you restrict yourself to a specific k, and k is greater than 1, so sigma sub 2 of n, sigma sub 3 of n, etc., where modular forms turn out to be really, really helpful. Ironically, the more natural function, right, sigma of n feels like a much more natural function that, sure, of course, societies are going to come up with, take the sum of all the divisors of a number and see what happens. But somehow that one turns out to be tougher. And that has to do with the lack of well-behaved modular forms that have coefficients involving sigma of n in a straightforward fashion.
But
and there are ways to bootstrap that, but they're limited.
I feel like this happens a lot in science. Sometimes it's very hard. The phenomenon which is right in front of your face might be hard because actually there's a couple of things going on, and you need to isolate what's happening before you realize. People who tried to understand fire. Well, there were multiple chemical reactions. Why is if you just had the single chemical reaction, it would just be a blue flame or something. And
yeah, right. Fire. That's a good example. Fire, right, is very complicated, right? And even when we teach fire, actually in high school chemistry classes, we actually sort of oversimplify the stoichiometry and a bunch of other things. If I have a minor hobby of interest as a complete amateur in rocket engines and rockets, and if you go try to open the chemistry books about chemistry about those, the complexity is so much beyond anything you saw in an AP Chem class. It's astounding. And to some extent, you have to wonder, like, how did people ever figure out some of what was going on here? And part of it was they started trying to understand things like burning wood, and turns out burning wood is really complicated. Yeah. But eventually someone found like, hey, burning like hydrogen or methane or just some other reasonably simple stuff is relatively easy to understand, and that helped.
I actually, because of my obsession with this history, I did look a little bit into this Norton anthology or the history of chemistry or something. Really interesting stuff that I never did, for people experimenting. First, they mixed all the different bodily fluids, and they noticed that there were two groups, and if you paired them off, they would bubble. The one from the acids and the bases, essentially.
Yeah.
And whatever. So, but just to get back to your ambition, so I guess you said the techniques that you don't really use. I don't know the techniques that you do use. I don't know what leads you to think that you will solve. You say you're not going to solve the odd perfect number problem.
I don't think we're anywhere near. I mean, look, my ambition there is not to solve that problem. My ambition is twofold. One is to help ask enough other interesting related questions that other mathematicians say, hey, let's go think about those questions. And two, that in 1,000 years, we finally have enough techniques for this, that one of the footnotes will be building on work of Zelinsky. I'll be happy with that.
Oh, but that's, we both had careers that possibly did not go exactly as we wanted. And, you have to be somewhat attentive to this issue. That's not enough for me, is what I'm saying. I can't.
Yeah. I think we have different ambitions. I mean, I'm working on other problems also. So there are lots of other things, so this graph theory thing. I've also worked with integer complexity, which is a lot of fun.
Oh, I've heard about this integer complexity thing. I have more problems with that, by the way.
Oh, but that's actually much more natural, I think, actually, in some respects. I would assert that I'm not sure the odd perfect number problem, if you like redid history, would necessarily have gotten the prominence it did. I think that if we meet aliens, I'm reasonably confident they'll have thought about, if they're thinking about math at all in a meaningful sense, they'll have come up with similar integer complexity problems. I think it's a very, very natural set of questions.
Well, there is a trend. There are a lot of people, the influence of computer science and mathematics has led to a lot of good mathematics, I think, in discrete math and graph theory. I don't know about this integer complexity issue, but I guess, I would say if you pick a problem, you've got to know that it's worth solving and that you have some ability to solve it. And the thing that I was mentioning in that previous video is that I really wonder about someone who is going to work in a direction where the techniques are somehow, in advance, they're not capable of really solving the problem.
I mean, so here's part of the difficulty, right? Is we don't currently have techniques which can solve the problem. Hopefully we'll develop techniques which do. Right. And look, so that's, part of that is, okay, we need to start somewhere, right? If we always say we're not going to touch these problems at all until we already know we've got techniques which have a decent chance of solving it, you may just not get there.
But there are always problems. I always try to find, what's right at the limit.
Yeah, no, I think that's a good attitude, right? And so in this case, right, I would say, look, the attitude isn't necessarily show there are no odd perfect numbers, but show there are no odd perfect numbers of specific forms, right? And we can often do that. So a lot of what I've done is, ruling out certain classes or showing new types of inequalities, relating odd perfect numbers and the size of their prime factors, the number of distinct prime factors, and so on. And one of the things I've also tried to do is, for lack of a better phrase, rationalize the approach of the mathematicians who are spending time on it. So let me.
I don't know if that's such a worthwhile endeavor, but okay.
I mean, it sounds really arrogant when I say it that way, but let me explain what I mean. So there is, despite the fact that I said earlier that this is a problem where, most mathematicians aren't really thinking about it a lot, there are still a lot of papers on the topic. And a lot of those papers prove results which are not really took a lot of effort in, but which cannot solve the underlying problem in a much stronger sense. So here's what I mean. So there's a theorem due to Euler, which says, almost so many things come back to Euler, that an odd perfect number needs to be of a certain form. I'm not going to say that form because it's hard to say verbally, but people can look it up.
But you mean in terms of its factors, or in terms
exactly, in terms of its factors. Okay. Actually, fine, I'll just say it needs to be a prime p that's 1 mod 4 to power that's 1 mod 4, and then times a perfect square, which is relatively prime to p. That's probably hard to hear verbally, so again, people should just look it up. Okay, but one of the things is, so there are lots of papers that have proven things like an odd perfect number must have like at least 7 prime factors, 7 distinct prime factors, at least 8 distinct prime factors, at least 9 distinct prime factors, etc. Or it needs to be at least 10 to the 300th, 10 to the 1000th. I think now 10 to the 1500th got done, and I believe from my conversations with Occam a while ago, I think Pascal Occam is now up to 10 to the, I think, 2,500, which is an obscene.
Somebody's still doing this, I guess.
What?
Somebody's still doing that kind of work.
Yeah. Okay. But here's the, there's similar things with the total number of prime factors, etc. Here's the thing. All of these results are weak in the following sense, which is
multiple senses.
Right. I mean, multiple senses. But one of the things that these results are all weak in the following sense is let's count all of the numbers which are less than or equal to x and satisfy Euler's criteria. Criterion for a potential. So it could be a candidate odd perfect number, and let's put that in a denominator, and let's put in the numerator all of the candidates for Euler's thing, and that also meet whatever thing you've proven about it, right? So add that new criterion. So for almost lots and lots of papers out there, this ratio as x goes to infinity is 1. That is, they are ruling out very small sets of candidates. Right? We are never going to prove the result, right? If we do care about proving the no-odd perfect numbers, we're never going to prove the result by any finite number of those.
Yeah.
Right? Because you've just ruled out a bunch of, in some sense, zero density sets. Yeah. Great. Not very, but they're doing very good math. But if you do care about that problem, and so I actually introduced in this paper, in a paper that's going to be hopefully, that's been accepted recently, is hopefully going to be published shortly, this idea of this weak and strong restrictions here. And one of the things I actually say in the paper after I've proven a bunch of things, and then, hey, I now have a section where I get to wax philosophical, is, hey, we should be aiming for strong restrictions.
I mean,
and so one of the things actually and that's something I think that needs to happen if we're going to solve this problem, is people need to say, hey, let's try to come up with a lot of strong restrictions if we can.
I agree. Maybe even those strong restrictions might not be enough. I'd be I'd be aiming for the kinds of things that might shed light on those adjacent problems, probably.
I mean, there's a lot of fun adjacent stuff to do, right? So, but I'm happy to work there. It's a
Are you hoping like Yitang Zhang, you'll deliver up at some point this paper, the world's going to take notice? And
look, I wouldn't mind if that happened. I don't think it's likely. I'm certainly not counting on it. And I'm pretty happy with where I am. So even if that did happen, I'm not sure I'd change what I'm doing for a living at this point.
I see. That's nice to hear. Because I saw that movie, Mr. Holland's Opus. He didn't want to be teaching high school. He wanted to be a professional.
Yeah, I think he's a fictional character.
It's a real, it could happen to people, and it does.
I also have to confess, I've never actually seen the movie.
Never seen the movie. Supposed to be an inspirational movie, how he learns to, love these students. They're for 30 years.
But
whatever.
No,
anyway, but this didn't have anything to do with your thesis, right? Your thesis.
No, my thesis was on counting art and representations, which are these representations that arise in these Galois theoretic contexts. And I'm not going to be able to give a reasonably short.
Okay, but I'm just wondering, so you did something else. I know that you were thinking about these odd perfect numbers even before.
Yeah.
And I wonder, you decided to go back to them. Did someone ever tell you don't do this work of this problem?
I don't know if anyone's ever said that explicitly, but certainly the people have been like, this is not necessarily what you should be focusing your time on. And frankly, for a long time, I didn't, right? For grad school, I tried to focus on do other stuff, art and representations are part of, that sort of core structure of respectable mathematics, adjacent to the Langlands program as every all good things are, et cetera.
Do you have any thoughts on the state of number theory today? Where it is,
I mean, I'm not sure I've got strong feelings on it. I do think that I will say, and this may come from my own biases and I understand the techniques better, I do think there's a real problem today that people are willing to jump to very high-powered techniques before they go to elementary ones often, even when there are simple elementary ones. And I think that there are, frankly, a lot of examples where there are good elementary approaches to things and a lot of people just don't go to them or don't think about what they can do. So I'm going to use an example, and I hope David Rorlick isn't going to mind this because he's going to come up in this example. So I was taking a class with David when I was in grad school, and he commented, we were doing something involving Chebotarev density. And so he noted that as a corollary of Chebotarev density, you get that there are, for any given polynomial with integer coefficients, there are infinitely many primes p where P divides the polynomial, some value of the polynomial. Right, assuming it's non-constant polynomial, so it's not silly. Right, so, and he said, was it a constant? He said, what? Sorry, anyway, so, so you have a polynomial like Q of X with integer coefficients, and the claim is that they're infinitely many primes P such that P divides Q of N for some integer N.
All right, I think I know what you're saying. I'm not familiar with that result, but.
Okay, so the point is, he said you need Chebyshov density for it. And I spent about 5 minutes thinking, I don't think you do. And in fact, you can, with only a teeny bit of work, modify Euclid's classic argument that there are infinite many primes to prove this result. Really, it's like 1 page or maybe less.
Something strikes me that that's not the important result. That's not what that Chebyshov density. That's
right. No, Chebyshov density tells you much, much deeper things, and it's although a lot of it gives you a nice corollaries. But the point is the fact that he had this, the classic, cannon to kill a mosquito, but it wasn't just using a cannon to kill a mosquito. It was a cannon used to kill a mosquito where you could have used a fly swatter. And I think this is not an uncommon issue. He actually said after I said to him, I think you can just do it this way. He's like, oh, I didn't realize you could do that. And was actually very gracious about it. And then they proceeded to email the whole class and be like, Josh said you can do it this way. Here's the proof, which is nice. Feels good when that happens. But I think that there is a common problem in number theory in general, where people are very quick to go to, I would say, to L functions, zeta functions, and all these, deeper methods, when they're often, and they don't necessarily understand the elementary methods as well. And those are techniques which are useful and, and helpful. And I will say in that regard, there's one book which is absolutely wonderful in this regard. So Paul Pollack wrote a book, Not Always Buried Deep. And it's about using elementary methods to do like interesting, really non-trivial number theory. I believe the subtitle of the book, it's Not Always Very Deep, I think, a second course in elementary number theory or something like that. But it's a wonderful, wonderful book. And I will say that the author is Pollack, Pollack, and the title of the book is if I'm getting the title exactly correct, I think is Not Always Buried Deep.
Not Always Buried Deep. I can now put a link, now I'm an Amazon associate. I can put
so you can get a link if anyone clicks through. Yay. Hopefully someone will give you a commission for that. Then. It's a good book.
But you know what? But that's something odd about what you're saying. I don't know if I agree. Of course, I agree that people should learn some of these elementary methods. Okay, I'm not, but actually as a methods, you got to be you're a professional mathematician. You got to know the high-powered techniques. And by the way, even if something could be done by these elementary methods, people will take more notice. If people will regard it as a better result if you use the high-powered techniques than the elementary techniques.
I mean, that I think is also a problem of itself, right? That connects in us, right? Is that we don't necessarily evaluate the strength of results based on how much insight they give us, but sort of, how high-powered are they? And I've actually seen an example or two of this occurring where, I actually had a conversation with someone a few weeks ago who will name anonymous, and I mentioned a certain specific result about a average value of the variation on the divisor function, counting the number of divisors and the sum that someone proved recently. And they were like, oh, that's very interesting. And how do you do it? And I started outlining how it worked in this completely, essentially, almost 100% combinatorial fashion. And they lost all interest. And part of why they lost interest was because they were obviously expecting that I was going to do something involving zeta functions, and involved very, very little of that. And so I think there's a problem there of actually your result doesn't involve these high-powered techniques, so we're going to pay less attention to it. Maybe a problem.
Yeah, but you understand why people do that is because they, it's not so much these results that are important, it's techniques they can apply to their own problems.
Right. If you're interested in a different sort of problem that, does really need those high-powered techniques, then seeing how they get used somewhere else is helpful for you. Yeah. That's definitely part of that.
My view is that people go to too much abstraction and too general a set of concerns when there's a much more concrete instance that is already full of, huh?
I said that might also be a problem. But yeah, look, to some extent, this may be sour grapes, right? So I can understand some of the basic analytic techniques, but I don't really understand them nearly as well as I should. And similarly with these abstractions, right? When people start doing very deep stuff involving, n categories, like I understand what a category is. I can recite the definition of a two-category probably if you give me a minute to think about it, but like I don't understand how to use it. And so part of this may be, sort of sour grapes on my part for not really being a good enough mathematician to really get how to use those techniques well.
Oh, that's okay. No one's going to give you any flack. I have no clue what is something with a category with a number in front of it, and I don't care. So, okay. And I think of myself as a major league mathematician. But the other techniques, though, yeah, I do think are part of serious number theory. I mean, I really like this book by, how do you say this guy's name? Ivanich?
Ivanich, I think I know. What's the name of the book?
Ivanich and Kowalski.
Yeah, I think you're pronouncing it close to correct, but I could be wrong. So
that's given me a lot of stuff to go on in a couple of different directions. I don't know if the kind of stuff you're talking about is at all related to anything that happens in there.
Ivanich is involved, if it's the person I'm thinking of Iwaniech.
I don't, there's no H.
Okay, yeah, I've done the C then. Anyway, yeah, so he's actually one of the people who's done some fantastic work with sieve theory in the last 30, 40 years. So I would bet at least some of that sieve theoretic stuff is in there, would be my guess.
And so you're not interested in pursuing, what are the other major threads in number theory? I'm still trying for my own, to figure out what was going on in that proof of modularity. But even though that's in a language that's very different from the kind of math that I know, I don't know what else, what are the big ideas. I do like all this stuff, the connection between the zeros of the Riemann zeta function and random matrices. And
that's one of those things I really wish I understood better. And I really haven't had the time to really sit down and really understand the underlying ideas.
I think there are good things in Diophantine approximation.
Yeah, there's a lot going on in Diophantine approximation. That also is one of the things that ties into a lot of other topics again. So there's a lot of, look, one of the things that sort of I see as part of, I'm not the only person to say, is good mathematics should build bridges, right? The more you see connections between this connects this other area of math that wasn't obviously connected to, that's good. And I think part of the appeal to some of these sort of abstracted techniques is that they really do feel like they're building a lot of bridges between different areas. So, and one of the obvious example, which I'm struggling to understand now, is so Dustin Clausen's recent work with Scholze. I was
just about to bring this up.
Yeah, but that's fantastic example of like building bridges between like a whole bunch of different areas, and like I hope that someone will write like a yellow book aimed at first year undergrads. I mean, not first year undergrads, sorry, first year grad students, a first year grad student level version of their work that I could understand.
Condensed mathematics.
Yeah.
Oh goodness, great. Well, you know what I did write to Dustin.
The tough bit I'm understanding is all these results somehow the special set of results they need involving the real line. So maybe you just say, we'll box that off and we'll assume that's already proven, wait to another book to get that. Here's the rest of it. But yeah.
I will reserve my final judgment. I want him on this program. I want to talk about that. I want to know what's going on. He and Peter Scholze are working on this big project that, my natural inclination, I'm skeptical about everything. I'm particularly skeptical of this project, especially I tried to look at, I saw an article in Nature about it, and that's what led me to looking up Dustin. And by the way, finding out that he had just done this interview on another channel. Do you know Maria Yackerson? And
no, I'm not familiar with
channel Math Life Balance. That's how I learned someone else had this same idea of talking to mathematicians.
Yeah.
And,
Well, yeah. Well, no, what Dustin has done, I mean, is very impressive. I don't know, look, Scholze is obviously one of the most impressive mathematicians alive today. But he's, but Dustin, but they've done it. The parts of what they've done that I do understand are very impressive. But I feel like I only understand a very small fraction of what they've done.
Well, I understand almost nothing. I tried to read it, and it just this is not even the language. It's like trying to read something in any other language other than English, which is the language I like. But even the aims, though, the aims bother me right from the start, because I look at Peter Scholze's notes, and he's like, he wants to take the analysis out of the kind of geometry that was really, I worked in Kähler geometry, and here is this whole, he's going to come up with a whole program designed to do all the things that I think are hopeless and pointless. So I don't know. I'd love to have these guys on my show, and
I think you'll have a better chance getting Dustin on than you will getting Peter.
Who knows? I'm on my way to the top. Well, I wrote to Dustin. We'll see. Maybe I'll write to him again. I'd like to know what they're thinking, but everything that they are thinking goes against every inclination I have about what.
Look, I think at the end of the day, if it works and it gives us a good insight to stuff, then it's the correct approach to some extent.
Insight. I'm all about problem solving. The value of some mathematics to me is whether it's able to solve a novel problem, a problem that you were already able to ask. It was already in the concerns that you cared about. It's not just about the new things you introduced.
Yeah, I agree. Creating abstractions for the sake of abstractions, I think for the same reason, is not compelling to me. But so I don't know enough about their work to know if it's solved anything yet, really. But I would say from what I do know of their work, which again is somewhat limited, I would be surprised if there won't be in the next 5 or 6 years, 1 or 2 reasonably concrete, pre-existing questions that they will have been able to say, yes, someone else already asked this question 20 or 30 years ago, and we can use our methods to answer it.
Are you aware, because even in the citation for Peter Scholze's medal, I believe it's not even claimed that he solved an original problem, that the problem, whatever it was in p-adic Hodge theory.
And the work with perfectoids and all of that, yes. I think people are in the process of using the perfectoids now to get good results. I'm not an expert on those things, though, so I'm really not, that would be one way you need to get Dustin in, or the other person who also was a PROMYS person. Do you remember Eric Knight?
I don't know. I don't remember.
So Eric Knight also has done some work with perfectoids and stuff, and is one of the people who's really done some interesting stuff on sort of, taking some of Peter Scholze's work and sort of bringing it downwards to useful things. So at least that's my impression. So that's he would be Eric. He's Eric Knight. He was Eric the K, if that helped. He may have post-dated you at PROMYS. Anyway, but he would be the other person to talk to.
Well, there's some numbers. Number theory is not my area. Number theory was my first love, because I was exposed to it at PROMYS, but it sort of got derailed as an undergraduate. I took a lot of math, and I sort of got attracted to the math of certain professors that I liked, and went into a very different area. I've sort of kept tabs on it a little bit, but any number theory that involves abstractions that come out of the Grothendieck school and philosophy is stuff that I just can't, wrap my head around.
One of the difficulties I have is I just don't understand it well, and I wish I did. I really don't think it's a reason to think that what they're doing isn't good work. I think it's more of a reason to wish I was smarter or had more time.
Smarter, but more time perhaps. I'm skeptical too of I like analysis. I can read. I love this paper of Gross and Zagier. That makes sense to me. But
so there is, I think, someone you would get along well. Do you know Jeff Ligarius?
That name rings a bell.
So he's a number theorist, although he does a bunch of other things at University of Michigan. Poor fellow is an expert on the Collatz conjecture, among other things, which means he gets all sorts of crank mail
It definitely.
I get crank mail too now. If you start working with odd perfect numbers, you get a decent chunk of crank mail. But he really gets a lot. Anyway, but he's done a lot of very good stuff independent of that. Like really all across the board, all sorts of areas of number theory and some other stuff. But he's someone who likes concrete things. And so there is a story. I was not present. This isn't this happened, but I've been told this story now twice by two different people. So who both claim to have been present. So I imagine it's true. And if not, it's a great story. And hopefully Jeff won't mind me telling the story. But the story goes.
Tell me the story.
The story goes that Jeff was at a thesis where he hadn't had a time to actually a thesis. He was on the committee for it. He hadn't had time. He was to be on this committee. He had replaced someone else at the last minute, so he hadn't had time to really look at the thesis. But it was a number theory thesis or whatever. And so as the person is doing their, going through their Beamer presentation, there are all of these categories and these arrows and these commutative diagrams, and it's getting more and more abstract. And about 18 or 19 minutes into it, Jeff raises his hand and says, excuse me, I was told this was going to be a number theory talk. I don't see any numbers. One person who, when I mentioned this story to them, said, well, the speaker should have, it's really mean to the speaker. I said, yeah. They said, it would have served Jeff right if they'd said, well, you look, there's a number at the bottom where the Beamer slide number is listed. But I don't think that's what happened. But, so there are certainly people who do that and do really good work, right? To some extent, I would say, I think of some of my interest in more elementary techniques, although not all of it, feels like it's in that sort of feeling of Jeff, is that things should have, or Erdős or Pomerantz, right? That things should have concrete things at the end of the day. But at the end of the day, we also want to develop abstractions and things and want to develop techniques that we can do more of. And if we can do more, and that requires abstraction, then we have to just sit down and learn those abstractions.
Well, it's odd how we're talking about a couple of different things. I guess I am big on the high-powered techniques, and I have very little interest in the abstraction and generalization and formalism. I somehow view you should look at the specific instance and apply analytical techniques. I somehow doubt that viewing things as part of in a broader framework ever actually helps you to solve the specific problem. That's my philosophy.
Well, look, one of the things that Grothendieck was unhappy about, and this is the opposite direction, is that a bunch of his conjectures and ideas ended up getting proven by using things much more concrete than he was expecting.
Of course, and if they were certain to, because that's how things get solved. It's
not quite, but but there is there's a tension there, right? Yeah.
So, well, this is one of the things. Maybe if you know more about this, you can help me. But he's given so much credit for these vague conjectures, when in fact all these conjectures were not done using. He has a philosophy.
That's part of one of the ones he was unhappy with, is that a lot of what went into it ended up not using his stuff.
Exactly. There's a lot of there was Hass's bound, and he had already done that in the 1930s, and had nothing to do with Grothendieck. And today,
it had nothing to do, but a lot of the high-powered abstractions he was hoping would be relevant turned out to be less so. Is my understanding, but I'm really not an expert on that stuff either, so I really shouldn't say too much about it.
Dwork, he's proved the rationality using p-adic.
And then Deligne comes in there somewhere in that story.
Deligne solves the thing, and there's a lot of of estimates on L functions and the Rankin-Selberg method. And so I was reading. I don't know Deligne's paper, but that's the thing. I sort of want to know that almost just as ammunition against the abstract people. Really, I should be using it to get.
I mean, I would think if I were going to be looking for ammunition, maybe I shouldn't give it to you. But if I were going to be giving you ammunition against too much abstraction, I think the obvious example would be interuniversal Teichmuller theory.
Oh, this is a joke. This is a complete joke.
Joke. Like, it went nowhere. It was like we have this giant abstraction, and it's like, well, can you recover anything? Maybe you could recover like hey, the only
tell our audience, because we have never discussed this.
Okay, so I should, by the way, say that my opinion on this, I was very relieved to find out after I had an opinion that Terry Tao had an almost identical opinion while this was ongoing, which made me feel good and made me feel not too bad about having the opinion I had. So for the audience then, so the ABC conjecture is this very long-standing elementary but number theory problem, which would have as a corollary literally, I don't know, maybe 50 or 100 things we want to prove come up as corollaries from it fairly quickly, probably more at this point. And so this fellow who, whose name I'm now blanking on.
Mochizuki?
Yeah, Mochizuki, who's a respected mathematician, put up on the archive this very long set of preprints, which used this technique that he introduced called interuniversal Teichmuller theory. And he claimed that it proved the ABC conjecture. These papers were borderline unreadable, and they involved this massive abstractions and such. And so one of the things people said to him is that, hey, maybe you can like get some piece out of this, because a lot of us are having trouble reading this. And it wasn't like Grothendieck, where Grothendieck is like stuff is well written. So like you can tell very early on, hey, it's getting really abstract, but the problem is more on my end. Whereas it seemed pretty clear that, you know, people who are used to high levels of abstraction had a lot of trouble with Mochizuki's writing. And so they said anyway to him, hey, could you maybe show using these techniques to get some smaller thing, like some natural things that might come out of something you expect to prove ABC would be like elliptic curves only have finitely many integer points, or, you know, or it was known that ABC implied that Fermat's last theorem is true for sufficiently large n. So maybe you could get that out without using, you know, the ABC, the full result. And Mochizuki's response was, nope, this either gives you ABC or nothing. There's like no middle ground. And then like people had a lot of trouble. And Peter Scholze, who we mentioned earlier, actually was one of the people who identified where they found like a critical problem in
and I give him credit for doing that. I mean, whatever else he did, you know, he's a respected person.
He spent the time going through these hundreds of pages of Mochizuki's stuff, which, I mean, given how important, frankly, I think Peter Scholze's other work is, I know you and I disagree with that, seems like at minimum not the best use of Peter Scholze's time. But I guess he's
anyone's time to read something like that. But I'm glad that someone with his position and status,
right, and I'll let Peter decide what's a good use of his time.
Yeah,
I think he is a better judge of his time than I am. But he found a critical problem where the result just did not work. And there's a whole ongoing drama because Mochizuki still hasn't acknowledged that there's actually a problem with his work. This has now been going on for years. But the problem is Mochizuki made this giant...
By the way, it was published. It wasn't in some Japanese journal, right?
Yes, there's a whole, but one of the things that was interesting there, right, is you had this giant abstraction. And you know, one of the initial hopes when Mochizuki was doing this, people were like, well, if it proves ABC, what other great things are we going to get out of it? And it turns out that halfway through your attempt to bring it down to this giant abstraction at a concrete level, it was a critical problem. And it looks like he's now constructed this entire edifice, as far as we can see, does nothing useful. Now, maybe in like 100 years, someone will go back and figure out something useful they can do with it. I'm skeptical. So, you know, so one of the dangers of like too much abstraction is you abstract away a lot and it just turns out it doesn't work very usefully.
Yeah.
But I think so one of it's tough there.
Well, this is, I could have told people not, look, math proofs that you put out there, it's not just about, oh, there is some, you know, you follow axioms and it's logically supposed to do something in the end. People need to be able to read it and take something out of it. You need to be able to tell people right at the front, like, what is the key idea? What is the technique? You know, what is the new, in my view, the new estimate, the new analytical technique that you were able to get something, doing something that other people had not been able to get before, that other people are then going to be able to comprehend and use.
Absolutely.
That's the thing.
I agree with you there. Central ideas, what is different, what can people use and build on? But I'll say something else, and I think that the Mochizuki thing with the inter-universal Teichmuller theory. What?
Mochizuki is his
Mochizuki, I'm probably butcher. I apologize to him if I'm messing up his name. But one of the other things that it also reflects is an additional problem, and this is something you need to be very careful about, like doing work like what I want to do with the odd perfect number problem. Is it's very easy when you're trying to prove something doesn't exist to confuse I've gotten a contradiction with I've made a mistake. And so one of the things that's critically important, and this is one where I really hope that any watchers who are young mathematicians take this for heart, is when you're trying to prove something doesn't exist, prove as much as you can about things you know exist, right? So break it down into lemmas, that this lemma says, hey, if this thing exists, then it has to have these properties. Prove this other thing. If this thing exists, this has to have these properties. And do that a bunch of times with things that you're reasonably confident actually exist. That way you can at least test them on concrete examples, and you don't have the same likelihood of, hey, I've made an error somewhere, and that error is what got me a contradiction. And only at the end, try to put those together to really get something that really shows the object you want that you don't think exists doesn't exist. And I think this is a journal, not just from a good writing standpoint, also is good for, hey, we like proving things about things that exist. If at the end of the day, you've given me a 30-page proof that shows something doesn't exist, I can't do as much with it. Whereas if you break it down into critical lemmas, and here's the central ideas, I can use maybe those pieces to prove things about other things which maybe exist.
I guess I'm not sure exactly what you're saying. Are you saying in a case where you don't know the truth of the conjecture, the thing you're trying to prove?
So let me use a different example, because this one used to be really popular until Andrew Wiles proved Fermat's last theorem. And even then, you still got it on occasion, was people proving these claimed elementary proofs of Fermat's last theorem. Because let's be blunt, they always were elementary, because these were people who had even less understanding of deep techniques than I do. And what you often would see is be like 20 or 30 or 40 pages of algebra, and they'd get a contradiction, and they'd be like, so Fermat's last theorem is proven. And part of the difficulty is when you write things that way, right, is it's very, very easy to get a contradiction that's really just I made a sign error, or even something slightly more subtle.
Yeah.
And so I think one of the things that's sort of good epistemic hygiene is when proving things, at least at minimum, when you're writing things out and your final version say, hey, I think I've got something people should look at, is prove as much as you can in a framework where you're proving things about things which we think which exist, which you can give concrete examples of. Okay. So don't prove something, about, if P is a prime that divides an odd perfect number, then blah, right? And prove something about, if P has a prime with the following properties that you're actually the ones you're using, then blah, and then see if you can hopefully find primes that actually have those properties, right?
Okay, I see what you're saying. I don't know that that's come up quite that way in my own work. I do know that I try very hard when I don't know something is true. If I think it's true, I think, you can't do, I have to work it from both sides. I do as much as I can to try to construct a solution, even if I think it doesn't exist. And either I show that there is, or I see what is the key difficulty, and then I come at it from the other way.
Right, and that's a really important thing. I think one of the difficulties also, again, with some of that this connects to, is that you have that option, right? Whereas if you're trying to just work always in the P as a prime that has certain properties and divides an odd perfect number, you're not going to find an example of a prime with those properties, because it probably doesn't exist, because there probably aren't any odd perfect numbers. But if you instead say, hey, I'm first going to prove just P as a prime with the following set of properties are the ones I really need, you're much more likely to be able to do that dual-sided. Can I prove this? Can I not prove this? Can I show that maybe, hey, wait, I've got a counterexample. Yay. Right? Counterexamples are nice. They tell us not to waste our time.
Mm-hmm. Well, there are a lot of people wasting our time with bad math papers, for sure. I want to ask you what a little bit going back to your teaching, whether you have now that you're a teacher, whether you have some different ideas about math education that you once had.
The truth is, I haven't been teaching long enough, I think, to necessarily have a lot of strong feelings about it that I think I'm well educated enough and have enough experience for. I'm sure in a few years, when I'm old and crotchety and yelling at kids to get off my lawn, I'll do that. First, I have to actually own a house rather than an apartment so you can yell at kids, but I'm looking forward to eventually being in that situation.
Well, I wonder, what do you think people should know? I guess I'm curious what you think that, you teach your students or in high school certain things. Now, some of them are quite advanced and they're going on to do some actual math. What do you think the general population should know about math, and what do people who are thinking about?
Oh, everything. Everyone should know everything. But I mean, obviously, we don't have time, and we have limited resources and intelligence and education and et cetera. But I mean, look, one of the ongoing discussions you have now is how many students should be taking calculus versus how many should be taking, say, AP stats or something similar, statistics, right? Basic statistics class, in a high school level. And there's a lot of good argument for one or the other being prioritized, and maybe prioritizing based on what majors they want. I'm not sure I have a strong opinion on it. To me, I almost think we spend too much time on some things that aren't necessarily going to matter as much. If we reduced how much trig we spend time on doing trig, I think we could live, we could survive. I think, it's, yeah, I mean, that would be the one, if I were cutting out something, maybe reduce the amount of trig, maybe, even though I actually love proving trig identities. I think that's a lot of fun, but it's not, we could do a lot of it in pre-calculus, and I'm not convinced it's that necessary.
Well, it's not necessary for the world today because we have GPS and whatever.
Right. I mean, and the reason why you don't need to learn, none of them are learning to use a sextant. If I ever have a year where I really have like an extra week somehow, and you never have that much extra time. If I had an extra week with pre-calc students, I think one of the things I would do would be like, all right, we're going to learn how to use a sextant. Or we're going to learn how to do like velocity made good, and and a bunch of other stuff that really uses those sort of classic trigonometry.
I would take students out at night and look at the sky and like plot a few stars and see what is the
it'd be a lot of fun. I mean, unfortunately, we have a limited amount of time. Right, there are lots and lots of things we'd like to do as students that we just don't have the time for. So we have to prioritize based on what other math classes they're going to take, what's expected of them, etc.
But you're right. Since they're not doing anything, they don't think at all about where they are in the earth. They're not doing navigation. They're not doing.
But they're also not thinking about the history, right? A lot of students are shocked when you say to them, "Look, the reason why there's a lot part of the history for why there's a lot of trig here is because Britannia ruled the waves." Like, students are just surprised by it. And one of the things I think is important there is that students don't necessarily realize how much of their curriculum is historically contingent. And it's not just in math, but math is obviously one where it's heavy in, right? It's easier to recognize in, say, English that, yeah, sure, what books we're reading has some degree of history connected to it, et cetera. And especially that one gets easy because there's lots of politics involved that I don't want to get into. It's less obvious that, hey, math, which is this area that feels like it's very abstract and it's absolute and it's universal, but which of the stuff we're decided to do or talk about, that has a lot of history to it. And I think that's something which they don't necessarily appreciate. Incidentally, if you had a version of your where did logs come from video that wasn't calculus heavy, because there's some bits of it that would calculus heavy. I would love, I mean, I'll give it the next time I teach calculus to some of my calculus students, but I'd love a version of that that would be written just with the pre-calc material. That did a good explanation. I could give it to them. I would absolutely love that. I think it might be doable, but you might have to think about that carefully.
I see. Well, you know, that is an issue that in these pre-calculus classes, you are expected to introduce the transcendental functions, which really do require calculus to
appreciate what's going on. The truth is, I think for most students, you'd say it's e to the x. E is the special number that you'll learn more about why you really care about it later, other than this thing involving, compound interest, which we're not going to actually convince you it really works, but we'll just accept some empirical stuff. And natural log is its logarithm. Students are generally happy and okay with that, but it does lead to issues. Yeah.
Yeah, students accept it. And so actually, I see two different, we're going in two different directions here. I do love history. I do like, I'm more obsessed with it now because, when I started to take teaching seriously, because I didn't like to just, what was in the book, definition, theorem, proof. I sort of know this came way later, and how would anyone have come up with this in the first place? Yeah. And when I started to learn about some of this and I saw the actual problem solving process, it was both more interesting to me. I feel like that's something students can grasp onto better. I don't know, because I haven't.
I mean, it's also, I think, worth for them to appreciate as an example that history and science is messy, right? It's often we develop stuff over a long period of time, and then we sort of pretend it was obvious all along. Well, of course, this is a logarithm. Of course, this is how a log behaves. And the fact is that like lots of very smart people had to think, and some of them went down directions which weren't necessarily the best, or came up with things and other people had to build on it and tweak it. And I think that that's an important thing just for understanding the history of ideas as a whole. Ideas are tough and complicated.
Well, there's certainly, so there's a lot of that could be interesting, that I feel like it should be a part of people's education. But on the other hand, when we started talking about like, what do people actually need today? Maybe a lot.
I'm not. By the way, yeah, I'm not sure, honestly. Like, right? I mean, look, honestly, like, I'm not sure what people need. It might be vary based on what they're going to go do with later in life. I mean, I would say one of the things, if I'm getting to list what do they need to do or what do they have, honestly, I think one of the things I'd want is more critical thinking. Right? I'd say, look, everyone. Right, everyone says critical thinking, then what do you mean by it as a problem? Because we all have different ideas. But like I would say one of the things I want would be like a lot more estimation, right? We do a little bit of estimation with like 7th graders or 6th graders, and then we sort of stop. But estimation, like Fermi estimates, is like I think we would, that. The other thing I want, and this is an important thing, is not just critical thinking, but here's the most important part about critical thinking, which especially is very easy to be critical about things you don't like or ideas you already don't believe in. And so one of the dangers in almost any time you try to teach critical thinking is that it will get selectively applied. And this applies, across the board, right? So you want to do like, a math thing and, like, well, I want to do back of the envelope calculation to show that, specific public policy I already don't like doesn't work. And you're like, well, that's, well, why don't you do it? What happens if it turns out you do? It does work, right? And so, or what happens if, maybe you should do it on a policy you do like and see if it doesn't work, right? What you're getting. And I think there's a real danger that we talk about critical thinking a lot, but we never actually tell people, look, one of the most dangerous things about critical thinking is you can tell yourself you're doing critical thinking, and critical thinking from the inside whatever critical thinking like feels a lot like partisan thinking. They feel very similar.
Frankly, every time I hear from someone that they believe in critical thinking, or I've heard so many people express this idea that, well, if only people were more educated, then their political views would more closely align with their own.
Of course, they'll obviously match my views personally if we do succeed at this, because my views are correct, right? I mean, there's an obvious problem here.
Those people need to do some critical thinking.
Right. Those other people, not me. I'm perfect. That's the way I am.
Yeah. Well, I wonder if it's occurred to them, by the way, just as a aside, couldn't it be that maybe people agree on all the basic things, but because they're in a different position, they just have conflicting interests? Like,
I mean, look, interests are complicated to people, right? And one of the difficulties also is that you have people who are not just, necessarily even interested, even if you give someone critical thinking skills, at the end of the day, they may not be interested in actually understanding the universe better. Their interest may really genuinely be, I want to support my tribe, my group and things, or might push my agenda, in which case you can't really help motivation-wise, other than just try to get them to change their attitude and approach. There is a book, actually, which recently came out, Julia Galef's, called The Scout Mindset, which I thought was quite good at this point. But it's a lot about that issue. And it says, part of it's about her realization. She actually professionally taught related critical thinking and rational thinking skills. And she realized as she was doing so that one of the difficulties was that even if you teach people the basic skills, if they're not really deeply emotionally invested in, I want to understand the universe better, and that's really my goal set, then it doesn't necessarily matter how much you give the skill set for. And so it's a fascinating book. It's certainly, and so it's, but yeah. So I think she has a valid point there.
I think we shouldn't be conceiving of math education to solve any, bringing people onto any particular political side, even though
Oh, except my side. I'm perfect again. No.
I know there are people who really have that agenda, by the way, but what about just you're preparing them? What about jobs and what they really?
I mean, that's something that honestly I think you would need to talk to an economist about, or people. And the truth is, I think things are going to change a lot in the next 10, 20, 30 years, just given automation and other changes. But I have no idea how they're going to change, which is great because I don't then have to be in the position of making a concrete prediction which is falsifiable. I'm just going to say, hey, things are going to change a lot. So I'm not sure. I mean, maybe there are other people who thought more about what those changes are, who have a better idea. But my guess would be that there are such people out there who have really thought about it, and I've read people who seem to have plausible ideas. But
well, shouldn't it at this point? It's already seems pretty clear to me that a lot more people could get a lot more use out of statistics than calculus.
I think that's. I mean, here's the question: here's why actually, probably yes. At the same time, here's why I'm not certain that it's actually even the right question, which is that almost most of the people who are going to take a class senior year of high school, that's either calculus or statistics, actually, I don't know if it's most, but certainly a very large fraction, are going to take other math classes in college, right? To some extent, right, calculus or statistics dichotomy sort of assumes this is their last math class. But if they're taking calculus in high school, chances are they're going to take more STEM classes in college.
Well, if
they're taking AP stats in high school, chances are they're going to be taking more STEM classes in college. And by that token, they're going to be probably taking more math classes. So it's not like it really ends there.
I see. This was sort of an issue that we discussed a lot at Cornell about, say, there's a lot of pre-med students, and they are only taking one math class in college.
Almost always exactly one, and then they move on, yes. But for people who aren't in that weird pre-med situation, which has a whole other topic, which I'm not actually really an expert on, other than to say I have opinions on it, but I know they're underinformed. But, right, most of those, right, so the point is, I would guess, although I don't have any numbers on this, that more than half of the students who take AP Calculus senior year of high school are going to end up taking a stats class either first year or second year of college. And I'd make the same guess that the AP stats students, more than half of them are probably going to take calculus sometime in
Did you do any statistics?
I did not. And it's actually one of my great regrets in life is I've actually never formally taken a true stats class.
That's right.
Helped tutor.
It was not something that was math majors were encouraged to do. It was never talked about. Like it was just in a different department, different program. It's like not part of math. And attitudes have changed a lot, I think, because of the advent, the growth of machine learning.
I think that's part of it. Look, part of it also is that this is, gets into things like history. At a lot of universities, the statistics department is a completely separate department from the math department for essentially to large extent historical reasons. And so one result is the classes don't count for a lot of things. And that's not, no, and so this is sort of an arbitrary distinction. You see it sometimes with computer science. You'll have some schools will have clearly mathematical theoretical comp sci classes that are in the comp sci department that aren't cross-listed, and you're like, well, what's going on there? And it's to a large extent historical, and I think there are deep history issues there that we're only beginning to address.
Well, I wonder, do you still do you recommend that people do math now? Is my
I don't know. I mean, look, so one of the difficulties, I think math is a lot of fun. So if you enjoy it, sure, you should do math. By all means, do more math. I'm not, look, one of the difficulties is, and it's, although it's happened honestly more slowly in some respects than I was expecting, is my guess is that eventually, probably in our lifetimes, the automated proof systems and, formal checking and all of that whole thing together might just render the humans obsolete.
Oh, I that's another. I doubt that in the extreme, but
yeah. But if it does, it's gonna really not be. You're not gonna be happy if you're the last person holding a bag with a PhD in math in 30 years, or if you've got tenure now, you're happy about it. But
the biggest problem is the lack of jobs. Okay.
I think lack of jobs, yes, but that's. I think they're right. Okay, so in the concrete here and now, obviously, a lot of people are going into math PhDs and thinking we're going to get, tenure line positions. And obviously, that doesn't happen always, right? You and me are both people who are not in the traditional trajectory there. But that's something I think, look, I think people are smart enough that, the math, that they can look at the numbers and see where things are. That said, I think we're also generally a somewhat arrogant bunch. And so probably lots of people are looking and saying, oh yeah, but I can be one of the ones who have really good results. And some of them are correct, right? Dustin Clausen, has done amazingly for himself. Although Dustin was always smarter than I was, and that was always very clear to me. So,
by the way, I learned in that interview that he does not, he doesn't really publish his own work, which is sort of incredible that he's managed to.
He's there's some interesting stuff there. I should actually watch that interview with him. I'll be interested. But the point is, sorry, there was a point. Hope we can cut that last bit out in the recording, so it's a little more.
People know they go into it. They can see the numbers. This is not actually, but when I was doing it, this is not something I was aware of. I was inspired from PROMYS and math, just all the way. It never occurred to me that this was going to be.
Right, but part of the thing is a lot of people do. The truth is, right, a lot of people do quite well for themselves, right? A lot of people go into industry or other stuff. I'm very happy teaching high school. So it's not like there aren't other positions, but people should be aware that there's not that likeliness to end up as a tenured mathematician.
I also think I would like to see some numbers on this, but I think it's hard.
I don't know the numbers offhand, but they're not great.
Harder and harder, not just obviously the tenured position thing is, people are clear, much more aware now of the way in which this is a pyramid scheme, sort of, or
I wouldn't say it's a pyramid scheme. I think there are systemic problems, though.
Well, Eric Weinstein, this is what he's talking about this. It's a system with embedded growth obligations, the way people take on so many students and they graduate so many PhDs, but the academic system is no longer growing and having positions.
Yeah, right. There definitely are problems there. Again, I don't think it's a pyramid scheme, but I think there are some systemic problems.
But also, I'd like to see some numbers on this myself. But I think those other outlets, which I heard about when I was a grad student, about people going into finance or other things, they are also starting to become saturated, and they're more discriminating about certain types of skills that they'd like to see. Now that they're no longer will take you just because you're a mathematician. because you've done some math.
I mean, that honestly, that's news to me if that's really moved that much in that direction. But I don't really know as much about those industries. So,
Well, see, that's
that would be.
I wonder if I'm, I know I love math, but what would I say to young me or something about, well, look, it's much easier. You'll have what the world wants is computer scientists or something, or something else. I mean, that's something I'm thinking.
But I mean, the truth is, for a lot of what they want in computer science is stuff where once you're a mathematician, it probably wouldn't be that hard to transition over, right? I mean, you can learn to code if you haven't, my guess would be that more than half of, pure math grad students end up learning to code at least one language by the end of grad school anyways. So, they'll learn to code, they'll probably do some machine learning related stuff, etc.
Yeah, but note how that skews the whole thing. It's almost like you're in a program ostensibly to do one thing where you have to focus your efforts very seriously on research, and yet you sort of also have to be planning an exit and doing an entire.
Yeah, there are difficulties. But I mean, I think there are people who, the people to talk to more about that, I think would be actually, people who actually are trying to do advising and things like that now. But I'm not really the person to think hard about that.
True, perhaps. Maybe bright people in high school. It's far off decisions they have to make. It's good that they're learning a lot anyway.
Look, right. I mean, look. I'm not giving them this. Certainly, at minimum, right. People can be an undergraduate math major and then move from there into all sorts of directions, right? That's, I think grad school is a very different question than undergraduate math major or double major, right? So, if you want more job opportunities, great. So you do the undergraduate math major and you do comp sci. There probably will be at least some overlap in what the two require anyways.
That's right. I remember, when I was starting, it was a lot more, well, there were just as many people who thought math and physics, but physics as it's.
Right, was a very common one when I was a student also. I don't know if it's still common. I don't know the numbers. So, I mean, to a large extent, this is complete spitballing because neither you nor I now have any actual concrete numbers on this topic.
Yeah, but I know that physics has the same issue with jobs. So
yeah, they have a similar situation.
What about the influence of PROMYS? Do you aim to recreate any of that style of learning?
Oh yeah, so that's very much an inquiry-based, more method sort of learning. I'm very fond of that. So when I've run the seminar with the students, I give them a problem set, to logic that often covers a lot of the material they've done, that they're going to be doing over the next few weeks, where they have to really work it on their own, encouraging them to work together in groups, to work on that. I've tried to do quite a bit of that, at least at that level. That's easier to do in the seminar. It's tougher to do that for other classes, though.
I see. PROMYS was my mathematical boot camp, and having those problem sets ahead of the lectures and working on something that way was something I'd never had before. And once I got into it, I somehow felt that I wished that I'd had that all along from the beginning.
I think it's pedagogically is a nice thing if it can be done well. One of the difficulties with it is it's a tremendous amount of work to set up well, and it's very, very easy to do it poorly. And PROMYS has the advantage of, I don't know when the Ross program was founded, but Ross was founded in 1960 something, maybe late 1950s.
Oh, I don't know the history of the Ross.
Okay, but the point is they're working off of a set of programs which were founded, 50, 60 years ago. It's easier to have a good idea of what works, what doesn't work in that very specific context. It's very tough sort of on the fly to say, hey, we're going to run this class this way.
Mm-hmm.
And it's also helpful in a context like PROMYS is that it's a summer program. So students are coming in there. They're not going to be upset that the class doesn't meet their expectations of what a math class looks like. Whereas you have to do much more expectations if, students are like, well, I took geometry last year, then algebra, now I'm taking pre-calculus. Why is this pre-calculus now doing this weird thing where I have to work out what the rules are myself?
Yeah, I can see that being a problem. Of course, I would love somehow to recreate that. I feel like very few programs are actually interested in training students, like actually making them better? That you can provide just the content of these courses, but not, you really want to make someone a mathematician, you need something like this program that we went to. And
I'm not sure. I mean, there are lots and lots of mathematicians who didn't go to PROMYS and haven't had experience at PROMYS and did just fine, right? I don't think it's a necessary or sufficient condition. I do think it's helpful. Yeah, I think it's helpful to have something like that. I especially think it's helpful because it really does, I think, engender a positive mindset, not just in math, but in general of how to really think about research and doing things. So one of the great things about PROMYS was the particips, the prove or disprove and salvage if possible. So you don't know if the statement is true or false. You're not told which way to prove it, whether to prove it or disprove it. And if you do disprove it, you're expected to come up with a similar sort of statement that somehow is salvageable. That's a true statement that you can prove. And that, I think, is closer to what doing research is like than almost anything else you do. Is you are working by nature on problems where you do not know the answer. You do not know if there's an easy answer. You don't know what direction it goes. And if you do find that the nice conjecture you wanted is actually false because of an ugly counterexample, or even a nice counterexample, the next step is to find ways, well, can you go around that counterexample? Can you, make still a true statement? And so that method is so close to what doing research is actually like.
Is that what you do with your students when you have the chance, when you teach?
So when I've done the seminar, I've done particips before. The truth is also, some students respond very well to particips and other students respond very poorly to particips. And it's a mix of what they do and what their expectations are. And even when you're doing like a proof-based class, it can be tough. I'm very fond of them, though. I'm actually, so next year I'm going to be doing the seminar on knot theory. And one of my things currently I'm trying to do now is come up with good particips for knot theory. I don't currently have a lot, but if you, any viewers, have any really fun knot theory particips, they're welcome to, send them my way.
Why knot theory? There's other stuff that's maybe more graph theory in general might be.
Well, I did graph theory this year, and we try to change from year to year what the seminar is, and we did number theory the year before that. So I'm doing it 3 years in a row. So I want to do knot theory. So I'm like, hey, let's do another topic. Basically, there was not that much deeper than that. If I could have done it again in a row, I actually might have done graph theory again because I think the graph theory went really well. And I think next year, if I'm still the person doing the seminar, we do have a few other people who are capable of running it, so I may not be. But the year after, if I'll probably go back to number theory, and then I don't know what I'll do the year.
Well, that's a very good. I feel like that's a very good way to start learning some serious math.
Yeah.
I guess that's the way I.
No, look, I mean, I started with number theory because it was the area where by far I had the most background in and most, ability to do it. So it's like, hey, after my first year doing this, we're going to do number theory. And then the next year is, again, it's like, this is my second year doing this. Okay, I just spent 2 years at a school that had a lot of graph theory. We're going to do graph theory. And now I'm feeling more of an idea of how things work. I can branch out a little bit more. And some of the teachers in the past have also used the seminar as an opportunity to learn a little bit along with the students. So they've done topics that they don't know that well, or learning with them, which can be a lot of fun. I have studied some knot theory before, so it won't be completely in that category, but it's a little closer to that aspect. And then we'll see what happens after that.
I guess do you use the PROMYS problem sets or something, or how does it compare?
So when I did number theory, I didn't use the PROMYS problem sets directly, but I did steal some of the problems. I stole a whole bunch of problems from them. I actually also stole a whole bunch of problems from when I taught number theory at Iowa State, which actually are problems I in fact stole from someone else who taught it there. I'm very willing to steal problems from a bunch of different sources. But yeah, so I have used so when I did the number theory, I did definitely do a lot of from PROMYS. The truth is, it would be tough given how much PROMYS influenced the way I think about number theory it would be tough for me not to. Like, my guess is that even if you didn't have a copy of the PROMYS problem sets in front of me, if you asked me to write down what are good problems for these topics, I'd end up finding out that I'd be writing down stuff that looks very close to the PROMYS stuff, even if it weren't deliberate. So I don't feel bad about, hijacking problems from there.
I once, I was teaching an analysis class at Cornell, and this girl came up to me at the end of the class and asked if I had gone to PROMYS. I wasn't wearing a PROMYS t-shirt, neither was she. She just picked up on something I said, something about
the approach or the...
Yeah, I don't know what it was. I don't know if it was this phrase about, the difference between something being simple or versus easy, or
You might probably use the quote, probably the whatever that quote is, simple is not easy. The other one is the quote about deepness. What's the one that Glenn is very fond of? There's another one. Simple is not easy.
I don't even know. I don't even know that that's what I said, but whatever.
Simple is not easy is I think one of them. He has another one or two that he's fond of. So my guess is, yeah, that was probably the tell.
Whatever it was, even so many years after, it must have been, it could have been 13, 14 years since I've been at the program. She picked up something about the way I said she saw
possibly notation also. I mean, there are a bunch of things that PROMYS does that are a little... Yeah, no, but that's do you remember who it was? I mean, maybe you should tell me afterwards, so it's not blurting student names off on random videos. But I'd be curious if it was just
the name. I'm not going to remember, but
all right.
Well, anyway, this was fun. We covered some stuff. Is there anything else you want to say?
Not really. I mean, I did actually have a little bit. I'd actually thought about doing a blurb for the graph theory works I did, but I think it's a 2-hour video at this point. I'm guessing that your readers are going to be your watchers are going to be tuning out after that long a video. So
this is the show. We're not really. This isn't an audience-friendly show at this point. I don't
think so. Well, hopefully your audience, you'll find your right audience for it. But
yeah, someday we'll figure it out. And we talk.
What you might be able to do is maybe do cut interviews into chunks and do each week all right, now what you've done 3 chunks from this person.
Well, there's a lot of things I could do that would be better. I like it this way. We're just having a conversation.
Yeah.
So it's all good. I mean, thanks so much for coming on.
All right, very good. Thank you, Dan. All right, have a good night.
You too.